Today's topic: generalized coordinates, Hamilton's principle, and Lagrange's equation from Some Physics. This is the highest frequency topic from your entire syllabus, so it's worth the extra care. Let's go slow, ground up, just like before. First, why do we even need generalized coordinates? Normally, to describe where something is in space, we use x, y, z, its position along three directions. That's called Cartesian coordinates. Problem: for some systems, XYZ is clunky or has restrictions. Constraints. Remember that topic? Example: a pendulum swinging on a string. The bob can't go anywhere in 3D space. It's forced to stay on a circle. The string keeps it at fixed length from the pivot. So instead of tracking XYZ separately, it's way easier to just track one number, the angle theta the string makes from vertical. That one number completely tells you where the bob is. We don't need the all three variables, like all three xyz. We just can do it with a single variable. That's what a generalized coordinate is. Any convenient variable, could be a length, an angle, anything, that fully describes the position or configuration of a system, chosen to make the problem simple instead of being forced to use xyz. We usually call generalized coordinates q1, q2, q3, etc. using the letter q instead of x, y, z. Just a label could represent an angle, a distance, or anything. A quick real life analogy. Think of a bead sliding on a curved wire. In 3D space, the bead technically has XYZ position, but because it's stuck on the wire, its position is really controlled by just one number. How far along the wire it has moved. That one number is a generalized coordinate for this system, much simpler than tracking three separate numbers that are all tied together anyway. Pause here. Does the idea of generalized coordinate uh, equals one convenient variable that fully describes position instead of xyz makes sense? Once you confirm, I'll introduce generalized velocity and degree of freedom, two small related ideas, and then we'll move to Hamilton's principle, which is the real derivations. Which is where the real derivation starts. Small step. Okay, yes. So moving on, generalized velocity. Quick builds directly on what you know. Remember, velocity equals a rate of change. Generalized velocity. Remember, velocity equals rate of change of position. We literally just did this trick twice already in the last topic in a different video anyway. Same idea here. Generalized velocity equals rate of change of generalized coordinates over time. If q is our generalized coordinate, q is representing position, right? So rate of change of position is velocity. Rate of change of generalized coordinate over time is generalized velocity. If q is our generalized coordinate, say the angle theta of a pendulum, then generalized velocity is just d by dt of q. So quick notation note: in mechanics, a dot on top of a letter is shorthand for rate of change with respect to time. It means the exact same thing as dq by dt. Physicists just prefer writing a dot instead of the whole fraction purely to save space. You'll see this dot notation everywhere from now on. Example: for the pendulum, if q equals theta, for the pendulum, if q equals theta, the angle, then q dot equals theta dot equals how fast the angle is changing, equals the angular velocity of the pendulum. Same concept you already know, just relabeled. Degree of freedom. Short, important definition, often asked directly as a 2 or 3 mark question. Definition. So, degree of freedom equals the minimum number of independent generalized coordinates needed to completely describe the configuration or position of a system. The minimum number of independent generalized coordinates needed to completely describe the configuration position of a system. In plain words, how many numbers do I need to fully pin down where everything is? Example to build intuition. A single particle free to move anywhere in 3D space needs xyz So 3 degrees of freedom. A bead stuck on a wire 1D curve needs only one number distance along the wire. So 1 degree of freedom. A simple pendulum bob on a string swings in a plane needs only angle theta, so 1 degree of freedom. A number of n particles completely free with no constraints. Each particle needs 3 numbers, so 3 n degrees of freedom for n particles. 3 n degrees of freedom. Rule of thumb connecting this to constraints, topic you already know. Every constraint you add removes 1 degree of freedom, because a constraint is a rule that ties variables together, reducing how many independent numbers you actually need. I need more intuition for this part. Anyways, for now we can move on. Formula short and exam friendly. Degree of freedom is 3n minus k, where n is the number of, wait, n was the number of particles, right? And k is constraints, number of constraints. So degree of freedom is 3n minus k. Pause here, quick check. Does degree of freedom equals minimum independent coordinates needed? And the example makes sense. Somewhat. We move to the real heart of this topic, Hamilton's principle, which is totally a new idea, not building on anything you have seen before. I'll introduce it extra slowly. Okay, so noted, flagging that as a some word so we don't lose it, but moving on. um Okay, so Hamilton's principle, a genuinely new idea. This one doesn't build on previous topics, it's a fresh concept. So let's go extra slow. First, a weird question to set the stage. Normally in physics, Newton's laws, we think force causes acceleration. So let's track position moment by moment using F equals ma. That's the usual way. Normally in physics, we think force cause acceleration. So let's track position moment by moment using F equals ma. That's the usual way. Hamilton's principle asks a completely different, almost philosophical question. Out of all the possible paths a system could take to go from point A to B, why does it take the one particular path it actually takes? Weird question, right? Think of throwing a ball from your hand to a friend. The ball could, in theory, wiggle up and down, weirdly zigzag, do all sorts of paths to get from your hand to your friend's hand in the same time. But it doesn't. It takes one smooth, specific path, a curve due to gravity. Hamilton's principle explains why that specific path gets picked out of infinite possible paths. The answer, nature is lazy in a specific mathematical sense. Nature is lazy in a specific mathematical sense, or efficient. Nature is efficient, maybe. Anyways, Hamilton's principle says the actual path taken is the one that makes a certain quantity called action as small or stationary as possible. The actual path taken is the one that makes a certain quantity called action as small or stationary as possible compared to all other nearby possible paths. Let's define action step by step. Step 1. Define the Lagrangian L. Before defining action, we need one more building block. The Lagrangian, written as capital L equals T minus V, where T is the kinetic energy of this system, energy of motion, you already know this, and capital V is potential energy of the system, stored energy, example due to height and gravity or spring compression. So kinetic energy minus potential energy. In plain words, like Lagrangian equals kinetic energy minus potential energy. That's literally the definition. Just subtract the potential energy from kinetic energy. Nothing more complicated than that at this stage. Not this is not the same as total energy, which would be T plus V, kinetic plus potential, adding not subtracting. Exactly. इसलिए तो मुझे समझ नहीं आया ये वाला part. Don't mix these up. Lagrangian uses a minus sign. Why? What does it represent? What exactly is it? One single pause here does Lagrangian ke minus p, one single number you can calculate for a system at any moment, makes sense. Once you confirm, I'll define action built using Lagrangian, then show you Hamilton's principle, actual mathematical statement. What exactly is. Okay, so this is exactly the kind of thing worth pausing on because ke minus p seems like great. Because ke minus p seems like a weird, almost arbitrary choice at first. Let's unpack it honestly. Is there an intuitive physical meaning to this? Honestly, not really, and that's okay. Unlike total energy, which has a clean intuitive meaning, total amount of energy the system has, the Lagrangian T minus V does not represent some physical thing you can point to and say this is the amount of x in the system. It's not a form of energy floating around anywhere. So what is it then? Think of Lagrangian less like a physical quantity like energy, force, or momentum, and more like a mathematical tool, a clever recipe that when you feed it into a certain procedure, which we'll get to, the Euler-Lagrange equation spits out the correct equation of motion, that is, tells you exactly how the system moves. So why does this trick work? Plain intuition, not rigorous proof. Here's a way to think about it that might help. So, kinetic energy represents the system's tendency to keep moving, change position. It's tied to motion, to doing stuff, to change. Potential energy represents energy that's stored and waiting, tied to position, resisting change, like a ball wanting to roll downhill due to stored gravitational potential energy. By subtracting V from T, the Lagrangian becomes a quantity that's large when the system has lots of motion tendency and small stored resisting tendency. And Hamilton's principle says nature picks the path where the running total of this quantity over time where the running total of this quantity over time is as small as possible, technically stationary. We'll clarify that words shortly. Analogy imperfect but helps intuition. Imagine T is like how much you want to explore or move, and V is like how much the terrain resists you. Lagrangian rewards the path where you get a lot of free movement without fighting against stored resistance too much. It is definitely philosophical, anyways. Nature chooses the most efficient such path. The real significance, this is important exam relevant part. Here's the actual payoff, and this is what you should hold on to. The Lagrangian is significant not because of what it physically means, but because of what it lets you do. You calculate T and V for your system using whatever generalized coordinates are convenient, angle, distance, whatever. You plug that Lagrangian equation into specific equation called the Euler-Lagrange equation. We'll derive or use this soon. Out pops the equation of motion, that is, in essence, exactly how the system behaves over time without ever needing to draw a force diagram or use F equals ma directly. This is the whole selling point of Lagrangian mechanics, and it's literally asked as an exam answer advantage of Lagrangian or Newtonian approach. For complicated systems, pendulum systems with weird constraints, multiple connected parts, figuring out all the forces, especially tricky constraints forces like the tension in a string, can be a nightmare. With Newton's method, with Lagrangian mechanics, you never need to know the constraint forces at all. You just need T and V, which are usually much easier to write down. Energy is a scalar, no direction vector headache. In one sentence, the Lagrangian itself doesn't mean anything physical. You can point to its power is that its shortcut formula that when processed through one standard equation automatically gives you the correct motion of a system, sidestepping the hustle of tracking every force. Okay, so move next. I think this took way too long for a little Lagrangian equation, and it provided almost nothing anyways. Moving onwards, step 2 is defining action. S. We now build one more quantity called action using Lagrangian idea. The Lagrangian L can be calculated at every single instant of time as the system moves, since T and V can change moment to moment. Example, a pendulum's kinetic energy and potential energy change as it swings. So L isn't just one fixed number, it's a value that changes over time, like a graph of L versus T. Action as the sum. Technically, the integral of L over the entire time the system travels from its starting point to its ending point, written mathematically as equals integral from time 1 to time 2 t1 to t2 LDT. Okay, so let's break down this notation piece by piece since integrals can look scary. So this symbol, the equals the integral symbol. Think of it simply as add up infinitely many tiny pieces. Just like sigma added up a finite list of terms like adding ke for particle 1, 2, 3, etc., this integral adds up infinitely many tiny pieces, in this case, tiny slices. In this case, tiny slices of time. So LDT equals at each tiny sliver of time dt, take the value of L at that moment, and that's the tiny contribution being added up. T1 and T2, the starting time and the ending time. In essence, we add up L starting from when the system begins its motion T1 to when it ends T2. In plain words, action equals total accumulated Lagrangian over the whole journey from start to finish. So we need action to be as smaller as possible, right? Just like you might add up your total spending over a month by summing up tiny daily expenses, action adds up the Lagrangian over every tiny moment of the journey. You do not need to know how to actually solve or compute integrals for this course at the exam level we are targeting. Pass level answers just need you to write this definition and manipulate it symbolically, which we'll do next. So don't panic about how to calculate an integral. That's bigger topic than what's needed here. Pause here. Does action equals adding up Lagrangian values over every time moment from start to end makes sense as a concept even without doing an actual integral calculation. Once you confirm, as finally state Hamilton's principle itself in words, and then in maths this is short, and then we move into actual derivation of Lagrange's equation. Yes. Okay, so good to know. I'll teach integral basics if we actually hit a point where you need to compute one for the path level questions here. You mostly just need to manipulate the symbol, not solve tricky integrals, so we'll likely dodge the heavy calculus. Let's continue. Step 3 is Hamilton's principle, the actual statement in words. Out of all possible paths, a system could take between two fixed points in time t1 and t2. The actual path taken is the one for which the action s is stationary and essence doesn't change for small variations in the path. What does it mean? So the actual path taken is the one for which the action S is stationary for small variation in the path. What does stationary mean? An important word, let's not skip it. Stationary is a specific maths word. Here's the plain language version. Imagine you are standing at the bottom of a valley, lowest point of a bowl shape. If you nudge yourself slightly left or slightly right, your height barely changes. It stays roughly the same because you are sitting at the flattest point, the minimum. That flatness where tiny nudges don't change the value is what stationary means. Similarly, if you take the true path a system follows and you imagine wiggling it very slightly, a tiny fake alternate path close to the real one but not quite it, the action as calculated for that wiggled path would be almost identical to the action of the true path. Small wiggles near the true path don't change as much. That's what makes it stationary. Mathematically, the stationary condition is written using something called a variation symbol. Delta S equals 0. So delta S equals 0. S is not changing much for like tiny what neighborhoods, I don't know. So delta S equals 0 and S was integral of L dt from t1 to t2 equals 0. Now in plain words, the tiny change in action caused by a tiny wiggle in the path equals 0. A tiny change in action caused by a tiny wiggle in the path. How does this represent tiny wiggle in the path? Anyways, so this is the mathematical heart of Hamilton's principle. You don't need to deeply understand the calculus of variations, a whole separate branch of maths. For example purpose, you just need to state this equation and know what it means in words as above. I didn't understand this equation. Why does this matter to us? This equation delta of integral L dt equals 0 is the starting point from which we will derive Lagrange's equation of motion, the actual formula you'll use to solve problems like pendulums, oscillators, etc. The derivation from here involves few calculus steps using something called integration by parts. Don't worry, I'll walk you through it slowly, treating it like a mathematical recipe rather than requiring deep calculus understanding. Pause here. The stationary equals tiny wiggles in the part don't change. The action part makes sense along the equation, this being the starting point. Once you say yes, we'll go through derivation, the actual algebra calculus steps to get from this equation to the final Lagrange equation. I didn't understand this equation actually. I didn't understand this. I think it is taking a lot of time. Totally fair. This is generally one of the most abstract ideas in the whole syllabus. Let's rebuild it slowly with a familiar example first. Let's step back to something you already know, finding a minimum of simple curve. You have done this in school. If you have a function, say y equals x square, and you want to find where it's at its minimal lowest point, you take the derivative and set it to 0. Why does this work at minimum point and also the maximum point, the bottom of the curve? The curve is momentarily flat. If you nudge x a tiny bit left or right, y changes barely to first order. That's definition of minimum, or more generally stationary point. Tiny nudges in input don't produce a change in output. You already intuitively understand this. Good. Now we are going to do the exact same idea, but with one twist. The twist, instead of nudging a number, we are nudging a path. In y equals x, for example, your input was a single number x and output was number single number y. You nudge the input number slightly, check the output changes. If the output changes in Hamilton's principle, your input is the entire path, literally the whole curve trajectory the particle traces out from start to end. Thinking of it as squiggly line on the graph of position versus time, your output is the single number the action has. So now instead of asking what the value of x makes y minimum, we are asking what path out of all possible squiggly paths from point A to B makes the action s minimum or stationary. Okay, get it. Let's make this concrete with a picture in your head. Imagine you're throwing a ball from your hand from point A at time t1 to your friend's hand point B at time t2. Draw this graph and time. Draw this as graph time on the x-axis, position on the y-axis. The real path the ball takes is one particular curve on this graph, a smooth arc due to gravity. Now imagine a fake, slightly wiggled path. Same start point, same end points, but somewhere in the middle the curve wiggles just a tiny bit differently, like a tiny bump added to the real path. For each of these possible paths, real one and the every possible wiggled fake one, you could in principle calculate the action as by adding up this at every instant along that specific path. You could in principle calculate the action as by adding up this at every instant along that specific path. Hamilton's principle says if you calculate s for the real path and then calculate s for the path that's wiggled just tiny bit away from the real one, the two s values will be almost exactly equal. The tiny wiggle doesn't change as this is exactly like how at the bottom of the y equals x square tiny nudge in x doesn't change y. That's what delta s equals 0 means. Wiggling the path slightly away from the true path produces zero change in action. The symbol delta has here specifically means a tiny variation of wiggle. It's slightly different symbol from the usual d which you use for ordinary small changes like dt, because here we are wiggling an entire function or path, not just a number, but conceptually treated exactly like the derivative equals 0 idea from y equals x square. Okay, move next, but I forgot actually one thing. How does addition or like integral of Lagrange makes up action? It's good instinct to ask. Let's ground this with some more familiar first. With something more familiar first. You already know one example. Integral equals adding tiny pieces over time. Remember, distance equals speed into time for constant speed. But if speed keeps changing, you can't just multiply. Instead, you break the journey into tiny time slices. Calculate speed for like across tiny time slice for each one and add them up all. That sum of tiny pieces is exactly what an integral does. Distance equals integral of velocity dt for little periods of time.
In plane words, at every tiny moment dt, the object moves a tiny distance at speed at that moment times the that tiny sliver of time. Add up all these tiny distances across the whole journey and you get total distance. Nothing mystical, it's just many small pieces added together to get one grand total. Now apply the exactly same logic through action at every tiny moment dt during the system's journey. At every tiny moment dt during the system's journey, the Lagrangian L k minus p at that instant has some value multiplied that value by tiny instant time, you get tiny contribution of action on that moment. I get that, but ये action कैसे बन रहा है मुझे बहुत नहीं समझ आ रहा अभी भी. Add up these tiny contribution across the entire journey and you get one single number, the total action as for that particular path. Why is that being called action? But why define action this specific way? Why sum up L, not something else? Honest answer, this is a definition, not something derived from deeper reason. But definition भी तो किसी वजह से ही होगी ना. Just like distance equals vdt is a natural sensible definition. Add up tiny motions to get total motion. Physicists defined action this particular way as the accumulated Lagrangian because when you apply the make this stationary condition to this specific quantity it mathematically produces the correct experimentally verified laws of motion. Newton's laws fall right out of it, as we'll see. Okay, so this is not a natural sensible definition thing, but it gets the maths right, so that's why we're using. Okay, think of it like action doesn't obviously meaningful thing. Action isn't obviously meaningful the way distance or energy is. It was reverse engineered. Physicists found that if you wait, think of it like this: action isn't obviously meaningful the way distance or energy is. It was reverse engineered. Physicists found if you define this particular integral sum of k minus p over time and demand it to be stationary, then you get the right physics. It works, and that's ultimately the justification. You don't need a deeper reason why to pass this exam. Just know the definition and how to use it, which we are about to do. Okay, so move next. In one line, action equals total accumulated k minus p added up in tiny slices across the whole time the system takes to travel from start to end, exactly analogous to how distance equals total accumulated speed added up over time. Does that make it clear? If yes, let's move to actual derivation, turning this into final Lagrange's equation. This next part uses calculus technique called integration by parts, which I'll walk through as a mechanical recipe. But I'm tired and we'll start part 2 in another video. So, or should I just complete it? I hope jaldi khatam ho jaye. Let's start the actual derivation. This has several small moving pieces, so I'll take it slow and pause often. Take it slow, lol. Setting up, what does wiggling the path look like mathematically? We said the real path is QT, and we said the real path is QT, some function of time. Remember, Q is our generalized coordinate. Now we create wiggled fake path by adding a tiny extra bit to it. So Q wiggled T is QT plus delta QT. Here delta QT reads as delta Q is just a tiny extra wiggle function, small at every point in time. Small at every point in time, and importantly, zero at the very start and very end. Why zero at the ends? Because all paths we are comparing must start at the same point A and end at the same point B, like the ball leaving your hand and reaching your friend's hand. Only the middle of the path is allowed to wiggle, not the fixed start or end points. Picture it like this: draw a real path as a smooth curve. Now draw a second curve that touches the real one exactly at the start and end, but bulges away slightly in the middle, like a slightly stretched rubber band. That bulge at each point in time is dqt. A quick necessary detour. What is partial derivative? Before we go further, you'll see a symbol like delta L upon delta Q, curly delta, ऐसे कुछ बोलते थे ऐसे, I don't remember. Not हाँ, not the curly d instead of straight d, which is called partial derivative. And here's the plain language meaning: the Lagrangian L actually depends on three separate things: the position q, the velocity q dot, and sometimes t. When we write delta or curly delta L upon curly q, वाइज डी वाई डी टी था या फिर क्यू ही था? लॉल, कितना ऊपर जाना है? एनीवेज, okay, so when we write this, we mean how does L change if I wiggle only q? How does L change if I wiggle only q while pretending q dot stays completely fixed or frozen? I.e., you only look at how one variable affects things, treating others as constants for that calculation. Similarly, dl by dq dot means how does L changes if I wiggle only q. Rate of change of Lagrange per this wiggle, right? I don't know. Anyways, similarly, this means how does L change if I wiggle only q dot velocity while treating q position as frozen? नहीं समझ आ रहा मुझे कुछ भी इधर. This is exactly like ordinary derivatives except you have multiple variables and you are only allowed to move one at a time. So you're only allowed to move one at a time, freezing the rest. You don't need deep mastery of this. Just recognize curl delta symbol derivative with respect to one variable, treating the others as constant. Okay, but I didn't understand this path. But मुझे थोड़ा सा तो idea था partial differentiation का. Anyway, so pause here, two things to confirm before we continue. Does wiggle path equals real path plus tiny bulge function which is 0 at the start and end make sense? Yes. Does partial derivative with respect to one variable freezing the others make sense? Little bit actually. Once you're good with both, I'll show you how this turns into this. I'll just move next because I don't want to waste more time. I just wanted to end 38 minutes already. Okay, continuing step, writing out delta s using the wiggle. We have s equals integral of L dt from t1 to t2 and L Lagrange इसमें ये क्यों लिखा हुआ है Lagrange पे? Lagrange was potential and kinetic energy minus potential energy, right? So q is position, q dot is kinetic energy, velocity, and t. When we wiggle the path, q turns into q plus del q. Both q and q dot change slightly because of position wiggles. Its rate of change velocity wiggles too. So L itself changes by a tiny amount, which we call del L. Using the idea of partial derivatives from before, if L depends on both q and q dot, and both wiggle slightly, the total tiny change in L is the sum of how much L changes due to Q wiggling plus how much L changes due to Q dot wiggling. So del L has two parts, del L by del Q and del L by del Q dot टाइम्स क्यू डॉट इन. ये कौन सी मतलब कौन सी मैथ्स यूज़ किया है, मुझे नहीं समझ आ रहा है. हाउ मच एल चेंजेस ड्यू टू क्यू विगलिंग and how much L changes due to Q dot wiggling. In plain words, this is just saying total wiggle in L, sensitivity of L to Q, total wiggle in L equals sensitivity of L to Q, how times how much Q wiggled. अच्छा ओके, प्लस सेंसिटिविटी ऑफ एल टू क्यू डॉट टाइम्स हाउ मच क्यू डॉट विगल्ड. मुझे नहीं पता मैथ्स कौन सी यूज़ किया, बट एटलीस्ट द इक्वेशन मेक्स सेंस. दिस इज़ अ स्टैंडर्ड रूल फॉर हाउ स्मॉल चेंजेस एड अप when multiple things are changing. Nothing exotic, just bookkeeping. Not delta q dot just means the wiggle in velocity, that in essence the rate of change of wiggle del q itself will come back to this. Shall I ask यहाँ पे कौन सी मैथ्स यूज हुई or should I just accept it? Anyway, so the tiny change in action becomes this because del L की जगह पे सब्स्टिट्यूट कर दिया है. Was it del L? Wait, so this was S because del S का फॉर्मूला है ना. नेक्स्ट यहाँ पर del S है, so del L हो जाएगा and del L was this. Okay, I just replaced del L inside the integral, which with what we found above, direct substitution, nothing calculated yet. Hamilton's principle says this entire thing must equal to 0 because we need it stationary. Okay, so as little change as possible, like this, almost equal to 0. So del S we want 0, so we put it equal to 0. Hamilton's principle says this entire thing must equal 0. The problem we now face, look at this equation closely. We have two different wiggle terms, del q and del q dot. That's awkward. We'd like everything in terms of just del q, a single wiggle, so we can factor it out and say, since this wiggle is arbitrary, whatever it's multiplying must be 0. What? Since this wiggle is arbitrary, arbitrary क्या होता है? Ever changing. Whatever it's multiplying must be 0. The second term, this is the troublemaker. It has delta q dot wiggle in velocity instead of delta q wiggle in position. We need a mathematical trick to convert this term, so it also has del q instead. That trick is called integration by parts. Pause here before I introduce integration by parts. A genuinely new calculus tool, so I'll teach it from scratch like you asked. Does the equation above make sense as total wiggle in action? Internal wiggle sensitivity to Q, yes. Okay. Once confirmed, I'll teach integration by parts as its own mini lesson before applying it, and it's already 43 minutes into a single topic. What the hell? Let's learn this tool from scratch as its own mini lesson. Integration by parts. Okay, so mini lesson, what is integration by parts? First, let's recall what a derivative of a product looks like. You learned this in school, the product rule. derivative of a product. Okay, if you have two functions multiplied together, say u and v, both depending on some variable, let's say t, the derivative of their product is this: d by dt of uv is u dv by dt plus v du by dt. In plain words, the derivative of u times v equals u times the derivative of v plus v times the derivative of u. This is the standard product rule. You have likely seen this before in school calculus. If it's fuzzy, just trust it as a rule for now. It's well known provable fact. Okay, now let's rearrange this rule. We can rearrange the product rule to isolate one of the term. Let's isolate u dv by dt. Then it becomes d by dt time d by dt of uv minus v du by dt. I just moved d du by dt to the other side by subtracting it from both sides. Basic algebra, nothing calculus y calculus c in this particular move. Okay, now integrate both sides. Now integrate both sides, add up tiny pieces from T1 to T2. Integrating both sides from T1 to T2. Okay. बस इंटीग्रल का साइन लगाया है. No changes. Key fact used here: integrating a derivative undoes the derivative. Integration and differentiation are opposite or inverse operations, just like multiplication undoes division. So, it would become what? dv by dt बस uv बन जाएगा क्या? Yes, okay. uv, and this also uv what? So integration of u dv by dt times dt, d by dt बाहर, dt यहाँ पे, and uv together equals, ये बस लेफ्ट हैंड साइड की बात रही है आई गेस, uv from t1 to t2. This funny bracket notation just means take the value of uv at time t2 and subtract the value of uv at time t1. It's like it's just evaluating the function at two endpoints and subtracting, not really solving an integral in a complicated sense, just plugging in numbers. Okay, so our final formula called integration by parts is what? इस वाले को किया था क्या वैसा ओपन अप, मतलब change this part, rest is the same. v du by dt v du by dt, yes, everything else is same, only ये वाला part थोड़ा solve किया है. So final formula called integration by part is this. What is this actually used for in plain words? बस हो गया, इतना ही था. What is this actually used for in plain words? This trick lets you move a derivative from one function v onto the other function u at the cost of a leftover boundary term uv and a minus sign. It's a transfer tool. नहीं समझ आया मुझे. If a derivative is sitting on the wrong function, for your purpose the integration by parts moves it to the other one. That's exactly our problem from before. We have a term with dq dot, which is literally dt by dq, the derivative sitting on the wiggle, and we want to move that derivative off the wiggle onto dl by dq dot instead, so that we are left with a clean dq undifferentiated, that we can factor out. Okay, let's review this integration by part. So this is normal product rule. then rearranging it, then taking its integral, बस फिर उसका middle वाला term change कर दिया है to this. मिडिल वाले टर्म में इंटीग्रल और डिफरेंशिएशन आपस में कैंसिल कर दिए, बट बाकी दोनों में कैंसिल क्यों नहीं किए, एंड हाउ इज दिस गोइंग टू बी यूज्ड, ये वाला पार्ट मुझे समझ नहीं आया, बट एनीवेज लेट्स मूव नेक्स्ट. Let's apply this directly to our problem now. Applying integration by parts to our troublemaker term. Recall our troublemaker term from before. मुझे मैं पहले वाली पूरी की पूरी इक्वेशन भूल चुकी हूँ, बट एनीवेज दिस फॉर द टर्म. लेट्स अज्यूम वी वांट टू मैच दिस अप अगेंस्ट आवर बॉक्स्ड formula. Okay, so let's carefully match pieces. Compare dl by dq dot del q dot dl by del q. इस वाले से मैच हो रहा है क्या? I guess this is the term. Notice कहाँ गया? Let's carefully match. Compare this with this. Compare this with u dv by dt. u dv by dt. हाँ ये भी सेम ही है. Anyways, notice del q dot is really d by dt of del q. d by dt of del q, i.e. the wiggle in velocity is derivative of wiggle in position. Makes sense. Velocity is always the derivative of position, so the wiggle in velocity is the derivative of wiggle in position too. So we match. dv by dt is d del q by dt, meaning v equals del q, and whatever is left is u. So now plug these into the boxed formula. u की जगह पे del q by q dot and v की जगह पे del q, जहाँ पर भी है पूरा सब्सटीट्यूट. I directly substituted u as this and v as this into every slot of boxed formula. No new calculations, pure substitution. The boundary term vanishes. Look at the first term. फर्स्ट टर्म, हाँ ये कैंसिल हो जाएगा आई गेस, पता नहीं. लुक एट द फर्स्ट टर्म. हाँ डी बाई डी टी कहाँ जाएगा? अच्छा आई डोंट नो अभी भी. Remember from way back dq is 0 at both endpoints t1 and t2. अच्छा, because we said the wiggle must vanish at start and end. All paths start or end at the same fixed point a and b. So this boundary term equals anything. So this boundary term equals anything times 0 at t2 minus anything times 0 at t1 is 0 minus 0 equals 0. It completely disappears. But how does this turn into this? अच्छा ये वाली term ना, मैं गलत से कंपेयर कर रही थी. This term right here is this. Okay, this becomes 0, vanishes completely. What we are left with is this. Notice what happened. The troublesome del q dot wiggle in velocity is gone. Okay, so notice what happened. The troublesome del q dot wiggle in velocity is now gone, replaced by a plain del q wiggle in position. Exactly what we wanted. The derivative got transferred into del q dot, instead wrapped in a d by dt with minus sign in front. Transferred onto this, instead wrapped in d by dt. इधर भी तो q dot है ही. How does this make sense? For 0 does this substitution plus boundary term vanishing because this is del q equals 0 at the endpoint makes sense. Once confirmed, we'll plug this result back into this equation from before and everything will finally collapse into famous Lagrangian equation. This is the last step of the derivation. Let's just do it actually. Yeah, should I ask? But the RHS. Let's clear that up quickly, then move on. You're right that q dot velocity still appears, but not as del q dot wiggle in velocity anymore. Let's distinguish two different things that both involve q dot. Del q dot, the wiggle in velocity, this is what we successfully eliminated. Del L upon a del q dot, sensitivity of L to velocity, this is just a leftover piece of the original Lagrangian itself, not a wiggle. Its normal mathematical expression could involve mass, velocity, etc. that naturally contains q dot in it. Same as before, even stated wiggling anything. Same as before, we even started wiggling anything. So on RHS we have this. This is just a take the time derivative time derivative of that sensitivity expression. It's allowed to contain q dot inside it. That's totally fine and expected. What we specifically eliminated was the wiggle symbol, not the letter q dot. Okay, so, array, this is like the curl q dot partial derivative, and this is del q dot. Del and delta, I don't know. That made me confused, like that confused me anyways. What we specifically eliminated was the wiggle symbol, not the letter q dot itself. Q dot plane velocity is just a normal ingredient of Lagrangian and will remain present throughout. Only the this del or delta, what is this called anyways, this wiggle part were being hunted down and simplified. Bottom line, mission accomplished. Every term now has this, not this, which was our goal. But ये तो same ही लिख रहे हैं. Every term now has this, not this. Array, sorry, this is like not, this doesn't have dots. Which was our goal. Okay. Final step, putting it all together. Recall our full equation from before, applying integration by parts. Before applying integration by parts, we had this equation with us. Now substitute in our मुझे मतलब ये ना पेपर पे लिख लिख के करना पड़ेगा. I completely forgot ये equation कहाँ यूज़ हुई थी. Anyways, recall our full equation from before, applying integration by parts. Now substitute in our new result for the second term. For this term, we are going to substitute. So integration is still there. This term is still the same. Minus sign bahar, and this term we have substituted. Both terms now have a common factor, del q. Factor it out. Okay, so del q dt. Here's the final logical leap. Del q is an arbitrary wiggle. It could be any small shape, any tiny bump function, as long as it's zero at the endpoints. The only way this integral can equal zero for every possible choice of del q is if the stuff in the square brackets is zero, is itself zero at every instant of time. What? It could be any small shape as long as it's zero at the endpoints. तो ज़ीरो एट द एंड पॉइंट्स, बाकी ये नंबर कुछ ना कुछ तो होगा. So if the whole term is 0, then this bracket has to be 0. Only the way for integral can be 0. It can equal 0 for every possible choice of del q is if the stuff in the square bracket is itself 0 at every instant of time. So this is 0, or written in the more commonly seen form, what, d by dt of this minus this equals 0. हाँ ठीक है ठीक है. This is the famous Lagrange's equation, Lagrange's equation of motion. This is the formula you'll actually use to solve every pendulum oscillator rolling problem going forward. And that's it.